Dzień dobry, nazywam się Neves, jestem badaczem we Francji i częściej... Okay, my Polish cannot take me very far, so I'll be continuing in English. Dziękuję bardzo za zaproszenie. So I'll be telling you about my experimental work in quantum network protocols beyond quantum key distribution. So basically it's in the title, but we'll be speaking about anything but quantum key distribution. But before that, I'd like to hijack this presentation to advertise a bit where I come from. So I come from France, here, and okay, you know Paris, and I don't come from Paris, so I come from this little town called Besançon, it's near the Jura. And so I'd like to give you a few reasons to visit, maybe someday. So it looks like this, so it has this kind of middle-age vibe. Here you can see the old town, it's surrounded by a river, it's called the Doubs, and this Vauban citadel that was built during the Renaissance. You can see it's quite green, it's actually the greenest city in France. So you can have quite some beautiful sights there, and a quite vibrant culture as well, which probably contributed to make it elected the second best city for students in France. So one more reason to come visit. We have some specialties there, of course, some cheese, some wine. You probably know that one is one of the most famous cheese in France. And we have a long tradition in watchmaking. It's considered as the French capital of time. And, okay, we have also some well-known figures who were born or visited Besançon. So I won't give you the name of these people, you probably can guess who they are. And I'll give the answers at the end of the talk. And here are some clues. So, a writer, painter, famous scientists, and inventors. You can already guess some. We'll see at the end. So, we also have a very long tradition in optics, which is why we have built a huge variety of fields in the optics department where I'm working right now. So here is a non-exhaustive list of the field of research we have. So holography, we've been pioneering in holography and wavefront engineering in nanofabrication for nanophotonics in particular, supercontinuum generation, photonics neural networks, and of course quantum optics, which is the research axis on which I was hired this year as a permanent researcher. So my own research focuses on photonic quantum entanglement and mostly its applications, potentially in the future, to real-world applications. So I've been working on polarization entanglements, so bipartite and multipartite, path-encoded entanglements with applications to quantum network protocols. And more recently, I've been starting to focus on energy-time entanglement. I heard it's quite your specialty here. And for applications to quantum detection of organic gases. So it's a project that I recently started and for which I acquired fundings, the QLOG project. But today I'll be focusing more on the quantum network part, which is work that I've been carrying out mostly during my PhD in Université, but which I've been carrying out since with continuing collaborations. So, the context of this work is, of course, the quantum internet, so potential future communication network, where tasks could be secured via quantum cryptography protocols. So, the most famous quantum cryptography protocol you all know about, I guess, is quantum key distribution, which starts to see application in the real world. So there was this famous video conference that was encrypted via quantum key distribution between Vienna and Beijing in 2018. But a quantum network could feature far more cryptographic tasks secured by quantum physics, such as, for example, sensitive games, anonymous communication, electronic voting, and a big variety of certification procedures. Some of these tasks, we call them quantum primitives, so they are building blocks for bigger protocols. For example, in electronic voting, you may have to design who's going to start the protocol. So I've been focusing on some of these building blocks. So first, remote with coin flipping. So the ability of two players who play remotely to choose a random coin, to agree on a random bit, sorry. And another protocol being the transmission of quantum information through an untrusted channel. So think about the quantum internet as like a bunch of quantum links between different nodes. These links may be operated by untrusted players, by malicious players, who may disrupt the quantum information, and we still need to be able to transmit the quantum information through these channels. So this is a very important problem. So before we start detailing all these two protocols, which are basically going to be the layout of the talk from now on, I'd like to acknowledge the colleagues with whom I had the chance to work on these two projects. So they were, or still are, all in Leipzig's quantum information team in Sorbonne Université. Some of them left, as I did, but it was in collaboration. And so, yeah, this work also was supported by the ERC, yeah. So, we'll start with remote quantum with coin flipping. So, I'm first going to detail the problem we are interested in. So, Alice and Bob are two remote players, and they want to agree on a random bit. So, like flipping a coin can fall on head or on tail. And the idea is if the coin falls on head, then Alice is going to win the game. If it falls on tail, then Bob wins. So, we also consider a game where Alice and Bob may be malicious, so they may try to bias the coin flip in their favor, knowing that each of them have a preferred outcome. They both want to win. So Alice wants the coin to fall on head, and Bob wants it to fall on tail. So this differs from strong coin flipping. This is what we call weak coin flipping. In strong coin flipping, they could bias in both sides. Oh. Still works? Yep. Okay. So, yeah, weak coin flipping because each player has a preferred outcome, but strong coin flipping, they could bias in both ways. So this is an important cryptographic primitive for many protocols, such as multi-party communication, online gaming. So think about starting to play chess. We have to agree on who's going to play white and start playing. So weak coin flipping could be used for such a game. Any protocols with leader election and bit commitments. And so there exists some classical solution for such a protocol. So here, let's see one. Alice and Bob could both flip a coin on their side. They get a bit, a random bit out of this coin flip. And then they send this bit to each other. Then they compute a logical addition, a logical sum. So they get the same bits, and so the coin flip is realized that way. The problem with these classical solutions, not only this one, but all classical solutions that were thought, is that they either need to trust a third party to perform the coin flip, or you need to have relativistic constraints. So in this protocol, there are relativistic constraints. The messages need to be sent at the same time. Or you make computational assumption. This is why a quantum protocol was recently designed by some colleagues of mine, so Mathieu Rosieux, Sabo, Denis, and Eleni, of course, which doesn't require any of these assumptions, and it goes basically like this. So this is the schematic of the protocol. May look a bit complicated, but there's 3 parts in this protocol. So there's the preparation procedure. Alice is going to prepare untangled coins, so she's going to keep one and send the other to Bob. So this way they have the correlated results, and they're both going to give the same results. Then there's the decision procedure. So Bob is going to flip the coin, and this way decide who's going to win the coin flip. And then most importantly, there's this verification procedure in which Alice and Bob are going to verify if the coin flip was not biased in the favor of the other. So if Bob wins, he's gonna let Alice verify the coin flip, and the other way around. If Alice wins, then Bob is going to perform the verification. This will enable cheat sensitivity, which is a property that was identified as a potential quantum advantage, because no classical protocol allows this. So we can detect a potential cheating player. And this is enabled by entanglement verification. So we implemented this protocol experimentally, and I'm going to detail this experiment. So first, we have the generation of the single photon. We need a single photon for this protocol. So Alice prepares the single photon. So she sends a powerful laser in the PPK-TP crystal, which generates a pair of photons. One of these photons is used to herald the other. So in our experiment, we had a maximum heralding efficiency of 66%, so meaning we have 2/3 probability of having a single photon when we detect its win. Then she's going to prepare an entangled state thanks to this single photon. For this, she sends this single photon on a tunable beam splitter, which mix the single photon with vacuum. Then she sends one part of the output to Bob. So one output goes to Bob, the other she keeps. And we have this variable optical attenuator to emulate propagation losses. Because remember, Alice and Bob are supposed to be remote. So now we have an entangled state. How this happens is that either the photon goes to Bob, or it goes to Alice. So we have a superposition of these two situations, which basically makes a Bell state. So in our case, it's actually a bit unbalanced because this X can be tuned accordingly to the condition of the protocol that we'll see later. But so they share this entangled state, which is basically the entangled chords that they need to flip. So then Bob is going to perform the coin flip, so he mixes his part of the states on another beam splitter, and then detects. So he has a detector here, and this performs the coin flip. This is the decision part. Now the coin is flipped. So if he detects something, then he wins, and if he detects nothing, then Alice wins. And then we perform the verification procedure. So for this, okay, I'm missing some part. Okay, so Bob detects something. So if Bob detected something and wins the protocol, then Alice is going to perform the verification procedure. So for this, we're going to have an optical switch to decide who's going to perform the verification. So if Bob wins, then Alice simply detects her own part of the state to check if she gets the same result as Bob. If she detects something, then it means that Bob lied on his flip. So he can be sanctioned for cheating. Now, more interestingly, if Bob doesn't detect anything, then Alice is going to send her coin to Bob. And Bob here is going to perform a verification procedure by making interfere these two parts of the states. And here, if he detects something in the first detector, DV1 here, it means that Alice prepared the state properly, and so she didn't bias the entangled coins. But if he detects something on the second detector, it means that the state at the start was biased in Alice's favors. And so Alice is going to be exposed as a cheater and can be sanctioned for this. So in total, we have 5 outcomes to this protocol. We're going to recap.
But it's still just single photon.
It's still a single photon,
Okay.
but we just don't know where it is. Okay? So we have 5 outcomes to summarize this protocol. Either Alice wins, so this happens if Bob didn't detect anything in his detector, and verified the quantum state appropriately. So we have a detection only in the first detector.
So all beam splitters are balanced?
So we're going to see, basically we have to tune them so that here the state is properly balanced with this, they need to be tuned together, basically. X, Y, and Z, there are conditions that we're going to see that decide which parameter we have. So Alice wins, that's the first outcome. Bob wins if he detects something in his detector and Alice doesn't detect anything on her side. Alice is sanctioned if Bob didn't detect anything here, but detects something in his second verification detector. Bob is sanctioned if he lied, basically, on his detection of the code. and Alice detects her coin on her side. And finally, the last outcome that we didn't consider yet is the abort outcome if we didn't detect any photon, so if the photon was lost. So there are requirements for this protocol to perform properly, and these are requirements on these 5 outcomes that I just gave you. And these requirements are...
Sorry, but what about the source? I mean, the source is untrusted or trusted?
So the source is owned by Alice. So Alice could bias the states in her favor. And this is why we have the verification procedure in the end. But when players are honest, we have these requirements that we want to minimize the probability of abort the protocol. So this goes by minimizing the losses, of course. There's a fairness condition, so it means that when both players are honest, they should have the same probability to win the coin flip. Then there's the correctness. It means that when players are honest, they should not be sanctioned. So we should minimize the probability of them being sanctioned. So all of these conditions, they are verified by minimizing the noise and losses in the setup, and of course by properly tuning the beam splitter. So these are the parameters X, Y, and Z that you saw in the protocol, in the experiment. So the hardest part was actually to minimize the noise in this, and you'll see why here. Because basically, this is how it looks, how the experiment looks, and you see here, we have the optical switch here. It's actually taking 400 nanoseconds to respond to the electric signal. So we have to delay the photons during this procedure. This is why we have these big fiber spools that you see here. And this makes this setup a 300-meter fiber Mach-Zehnder interferometer. So it basically acts as an optical microphone. So we're actually able to record the sound here. I don't know if it's going to make sound actually if I turn this on. No, it doesn't. So here it's supposed to make some music because we were playing some music during the experiment to record this, but apparently it doesn't work here. But yeah, so basically it hears everything in the room, particularly the different apparatus that we have, the cooling systems and so on for our superconducting nanowire single photon detectors. So we had to insulate these fiber spools, and this way we could minimize the noise power and increase the interference visibility, which is necessary to minimize the probability of Alice being sanctioned when she is honest. So we increased the visibility from 80% without insulation to 96%. This was actually measured classically. We saw when we were doing the actual quantum interference, we had a bit more than that. We had like 98%. So a few results on this protocol. So we first considered an honest player who were not trying to cheat. And so here you can see the probability of the different events. So Alice wins, Bob wins, or Alice is sectioned, Bob sectioned. So for these two outcomes, we should have a minimum probability because they are honest. And we should have the same probability of them winning. And so you can see here that the protocol is relatively fair and that it is correct. We have no, the probability is effectively minimized for sanctioning the players. And we tested this with different losses, which effectively relates the different distance of communication. So here we tried until 6-7 kilometers. So, but we still have a higher probability because of the losses in the setup. So these can be optimized by fusing, for example, the fibers. We had like a lot of connectors and so on. The switch, the optical switch, also added a lot of losses. And so the idea is that the idea to keep from this result is that actually if you minimize the losses, this abort probability goes to 0. Now, the interesting part is the cheat sensitivity, which, as you remember, is allowed by entanglement verification. So to test this cheat sensitivity, I need to give you a bit of idea, like some idea of the cheating strategies of the two players. So when Alice is dishonest, what she can do to bias the protocol in her favor is to change the quantum state here. So as Aho was asking me. So this source doesn't have to be trusted. So we can bias here. She could use states that are not single photon and so on. And the idea here is that if she doesn't prepare the state that she's expected to prepare, then Bob is going to see it during the verification procedure and she's going to be sanctioned. On Bob's side, his optimal strategy to bias the protocol is to lie on the coin flip and declare a win even if he doesn't detect anything. And in that case, Alice is going to notice it on her side because she's going to detect the coin as well. And so we can test that now. And we implemented the two dishonest players. So first a dishonest Bob, so who always says I win, I win, I win. And we can see here that he has a certain probability of being sanctioned, which of course decreases with the distance, because then Alice is going to need to delay the photon, and so it has more probability to be lost, and so she may not see Bob was lying. But this again can be optimized, and so this is.
So it's rather low probability.
Yeah, because we had a lot of losses. But it's still non-zero. And we'll see that there's a way to then enforce security because we even have a small probability. The idea is that if if Bob is scared of the sanction, then he's not going to cheat. Then we go to game theory. And then, it gets more interesting for Alice side, because here, optimal strategy is to bias the coin, so we can actually here try a simple strategy a simple cheating strategy, which means like we just bias the beam splitter, and then we see that the winning probability actually peaks for a bias that is lower than 1. It means that already having this probability of sanction, even without any deterrent, it makes her use a suboptimal strategy. And then we also have like a sanction probability that increases with the bias, of course. And so this limits Alice's cheating strategies. So we can quantify this by implementing her interest in cheating. So we designed this function of the different events to quantify this interest in cheating. And so we add this deterrent factor, which basically symbolizes the strength of the sanction. So she has less interest in cheating if the sanction is going to be strong when she's discovered cheating. And so with different strength, we can see that her interest in cheating peaks at a lower value of x, and so we can enforce in that way a stronger security by using this deterrent factor. And the same idea could be applied to Bob, and this is why, like, thanks to cheat sensitivity, so entanglement verification, we could enforce a stronger security in this protocol. So this concludes the part on weak coin flipping. So it was the first demonstration of quantum weak coin flipping, of experiment quantum weak coin flipping, which was a refined version of the recently proposed protocol. So we use path encoding entanglement and entanglement verification to answer cheat sensitivity, which effectively enforce security. And so future improvement should include minimizing the abort probability with better coupling and minimizing the losses.
So just to make sure that I understand, so this beam splitter that Bob uses for his check should be with such transmission that if he does not detect anything, then in the end, in the final interference, it's balanced, yes? The altitudes are the same,
yes.
So that you have perfect
exactly. This is exactly that, yeah.
Okay, so you have to choose both this beam splitter transmission and also this initial beam splitter.
We have to choose the 3 beam splitter together.
Yes.
This is actually the hardest part experiment, like, which took us more time.
But the last one will be balanced, no? The last.
I think the balance. Yeah, the last one I think is balanced anyway. Yeah.
But these two should be.
But then we choose the 2 others. Yeah.
Okay.
We can actually take a break here if you have questions on the quantum weak coin flipping. Then we're going to move to the other protocol, and you can find the paper on the Nature Communications.
I have a question. What's the probability of the wrongful sanction because you have dark counts in all detectors. So
it's almost zero because we were using a superconducting nanowire single photon detector. So the dark count rate was actually very low. It was maximum 100 Hertz. And then on top of that, we were gating the detector. So we had a pulsed laser which gated the detection. So the probability of having a dark count when we were actually performing the protocol was very, very low. And then, okay, there's that part. So the dark counts are effectively the main factor to wrongly sanction Bob. But then to wrongly sanction Alice, you could have a bad interference, and for this, what optimized the probability, what minimized the probability of Alice being sanctioned is insulating the spools, the fiber spools, to have a better interference.
And I don't think it's in the adversarial model here, but if there's third party that wants to get Bob sanctioned, that third party can introduce some light to to get Alice sanctioned Bob. Yeah.
So this is already adversarial scenario. If you have a player who wants to bias the protocol, he's basically playing on Bob's side or Alice's side, and like you could consider him as Bob basically. So like let's say if someone wants to bias the protocol in Alice's favor, then he could like just use the lights. Like Alice can already do that basically. So this is another work that I've been carrying out. Well, I started during my PhD, and it was only recently published. So I think it should comfort a lot of PhD students here. Like, we've been trying to publish this for almost 3 years, and it was very recently accepted in PRX Quantum. So very proud of finally presenting this work. So it's a transmission of quantum information through an untrusted channel. So it's actually a very general problem that's going to happen in a quantum network, where you try to send a qubit through a link, a transmission link, and it may be untrusted. It may be controlled by a malicious player. So I'm first going to make a classical analogy by telling you a little boat story. So now Alice and Bob are two people living on two sides of a sea strait, and Alice wants to send a message to Bob. So simple solution is to send the message on the boat, and then the boat is going to go through the sea strait, and Bob is going to receive it on the other side and can read it. The problem is they may be in the strait, there may be like a pirate who tries to disrupt this transmission and destroy the boat, and destroy the message by the same way, or even worse, it could flip the message with his own message, and so Bob receives a wrong message. So what can Alice and Bob do about this? Well, Alice could send emissary boats with a message that Bob knows and that he can check on his side. Then Alice can send her message, the actual message, in the middle of all these boats, so there can be like thousands of boats like that. And then Bob can check, so if he receives the reference, like the emissary message properly, and check all of them, then receive the message from Alice, and if he receives all the emissary message properly, then there's a high probability that the actual message was not disrupted. So he can know that the message he receives is actually the proper message that Alice tried to send. The problem here, because we live in the classical world, is that the pirate could obviously read all the message and see differences between these messages and actually notice which one is the message that Alice tries to send and not the emissary message, and could destroy or disrupt this message, which would be even worse because now Bob is even more sure that he's receiving the right message, but which is actually the wrong one. So he's fooled. But in the quantum world, we could actually use quantum bits for the emissary message, in which case, of course, if the pirate tries to measure this message and see them, then it's going to destroy the quantum state, and Bob can notice that. And this is the whole idea of the protocol we designed. So the quantum transmission problem goes as follows. Alice has a quantum bit now, so it's not only a classical message that can be seen, but an actual quantum bit, which can even be entangled with some other particle or another system. So we call this message roll I. So this is the message that Alice is trying to send. So she wants to send it to Bob, but on the way you have this transmission link, which is a quantum channel. So it's really a general quantum channel, which can be operated by a malicious player. And we take the most general form as possible. So it could even be lossy, with a transmission that depends on the quantum bit. So think, for example, of a polarizing channel. And it may even evolve through time. So meaning that every time we send a qubit through this channel, then the parrot may operate differently. This is what we call non-IID. So IID is when the channel behaves every time the same.
So the goal is to send quantum information, not classical.
Exactly. Well, it could be classical.
No, but your goal is here to send real qubit.
Yes.
Not some bits.
Yeah, we send a qubit, which could actually be entangled. We need to preserve the quantum bit.
And you don't have here any additive noise, yeah? You just have losses.
Well, the channel could be noisy. Like we say, it's non-ID, it can evolve through time. Noise could be a way to disrupt the information.
Okay, so it's something beyond just lossy channel. You can, like...
Yeah, it's lossy, like it's the most general form. And so, at the other side of the channel, Bob receives an output qubit, and is trying to figure out if it's the right qubit, if it's the qubit that Alice was actually trying to send. So the protocol goes as follows. It's basically going to be very close to the classical solution that I gave, but which doesn't work in the classical world, but in the quantum world it works. So Alice is going to prepare some emissary quantum states, some probe states that I call them, which are very close to maximally entangled Bell states, which is basically the emissary message. She's going to send it through the channel, and Bob receives, well, she sends one part of this bipartite state. Bob receives her state, the states at the output, and he wants to know if it's still the maximally entangled state. So for this, what they do is they verify the correlation, and they're going to check the violation of Bell inequalities. And they're going to repeat this a lot of times, a huge amount of times. So they're going to send it like one time, two times, and check the correlation every time. Sometimes it's going to be lost because we said the channel can be lossy. And in that case, Bob is going to declare the state lost and and just register this outcome. So we continue. And at a random position R, which is unknown to the pirates but known by Alice and Bob, Alice is going to send the actual message. So this is when Alice sends the message in this random and secret position. And then Bob is going to first check that he actually receives something. If he doesn't receive anything, then the protocol aborts. And if he receives something, then he wants to know if it's the right message. So he stores the message and continues the protocol. So they keep checking the entangled state. And then the protocol ends. And now we need to quantify this correlation and to evaluate if the state was good enough thanks to this correlation.
But so how Bob knows which one will be sent?
So they have to agree on this prior to the protocol. So this can actually be done in different ways. So either they have a secure classical channel, or they need quantum memories to store all the states prior to the measurement, and then they measure on their side. So you have two possibilities.
Okay, but isn't it enough if Bob just stored everything and just after communication Alice told him
yes
which one was which?
Yes, that's using, but he needs to use the quantum memories.
Okay.
Yeah, it's either. So we choose to consider, in our case, we choose to consider a private channel because we think it's less resource intensive. So, and also having all these quantum memories poses more security problems because these are all actual quantum channels as well that needs to be certified. So the problem loops. So we choose to consider that you have a private classical channel to communicate this random position. So then on all the measurements we did on the maximally entangled state, we check the violation of Bell inequalities. So you're going to have close to maximum violation of Bell inequalities with this epsilon here. And then some self-testing results tell you that if epsilon is very small, then the output state, the output probe state, is going to be very close to a maximally entangled state. And so thanks to that, we showed that if the probe state was properly sent, then the message was also properly sent. And so the protocol succeeds. The good thing about self-testing is that it's device independent, so you need to make very little assumptions on the measurement device. But in our case, we consider a semi-device independent scenario in which Alice's side is trusted. This allows us also to trust the probe state source. So the source input entangled state is trusted. Alice characterized it before the protocol. She characterizes also her measurement apparatus. And this way, this relaxes a bit the inequalities that we need to verify. So we don't use actually the Bell inequality, we use the nicer inequality, which is the steering inequality. And we built a security on top of that. And so for these self-testing results, I mentioned the article on which we were based on. It's authenticated teleportation verification in a noisy network from Anupama in Krishna. And she demonstrated the self-testing result in a non-IID setting, which is very important for our protocol. So I'm going to give a rough idea of the protocol security that we designed. On the main ideas, so two main ideas. The first one is that, of course, measurement breaks the entanglement and so the quantum correlation. So if the parrot tries to read the message and check where the probe states are, then it's going to break the entangled states and we're not going to see any correlation. Well, the correlation are going to be lower, so we're going to have a lower violation of Bell or steering inequalities. And so the message will have a lower probability to be certified. The other idea is that maximally entangled states sort of contained all quantum states, meaning that you can prepare any quantum state probabilistically from an entangled state. So thanks to this, if the channel behaves well on a maximally entangled state, then we know it's going to behave well on any other states. And this is where we can deduce the security bound, which looks like that. It's actually a simplified version because then you have to include the number of states that you send, etc., etc. But this is like the asymptotic version. And there are three terms which are important here. Here the channel quality, which is what we want bound. Here you have the input probe state quality and the output probe state quality. So basically, if you send a high quality probe state in the channel and it goes out as good, then you know that the channel is good as well and behaves properly. Here, there's also another term that I'd like you to notice, is that little t here, which is the channel transmissivity. And so it tells you that the less transmissive the channel is, of course, the harder the security is going to be shown. So you're going to have to send more states as well. So we also implemented an experimental proof of principle of this protocol using a similar setup. So it was actually the second generation of the setup that I showed you before for weak coin flipping. So here, this time, we generate photons still in a PPK-TP crystal, but this time it is in a Sagnac interferometer, which allows you to generate close to maximally entangled states. So we had 99.2% fidelity in average to a maximally entangled state. And these are the trusted probe states. Then the photons are coupled in the quantum channel here. So note that these two couplers here are on Alice's side. So because we consider a semi-device independent scenario, we can trust a certain part of these coupling losses. And this will allow us to have a more relaxed security and easier, which makes the protocol easier to implement, of course. Then the quantum channel here we implemented as a VOA, and we also allowed a possibility to flip the coin thanks to the motors, the wave plates. And then we have here the polarization analyzer, which allows us to test the correlation of Bell inequalities. Bob receives the output state, the output probe state, and we randomize the basis at. Oh, let's do this again. I don't have the same issue again. So we randomize the basis to test the variation of band inequalities. So the performances of this experimental implementation are follows. So we violated the steering inequality with a deviation of 1%, 1.5%. The transmission of the channel went from 22% to 47%, which was evaluated thanks to the routing efficiency. And then we had to test a billion states to send 1 qubit. So that's a lot. This is mostly due to the relaxed IID assumption. So because we don't make the assumption that the channel behaves the same way during the whole protocol. This is also due to the fact that the channel is more or less lossy and we have suboptimal probe states. So I'll comment on this number at the end of this part. But so the measurement time of this protocol to send 1 qubit went from 1 to 3 hours. Doesn't look very practical, does it? Well, we'll comment on that. So first, the results for an honest but lossy channel. So they go as follows. So here we have the minimum fidelity certified thanks to our protocol. So fidelity between the output message and the input message. Depending on the measurement transmission, so that we tune thanks to the variable optical attenuator. And you see here different curves in different colors because we have different amounts of trusted losses. So this is due to more or less trust that we put in the coupling on Alice's side. So the blue curve, of course, is when Alice trusted fully her coupler, so we trust all the losses, so they are completely unbiased. And the red curve is if like even the coupling losses are not trusted, and so these could involve some bias in the losses. So for example, a polarizing channel. And so we can see here that the more trust we put in the coupling losses, of course, the higher the certified fidelity, sorry. And the higher the channel losses in general, the lower the certified fidelity. Then we implemented the dishonest channel by flipping the message. So we implemented some random bit flip and phase flip. And we can see here that the minimum certified fidelity drops very fast with this probability of disrupting the information. And so the attempt of flipping the bits or the phase is detected as soon as it has like higher than 1% probability. So the protocol is of course highly sensitive to the disruption of information. So some perspective and conclusion on this part. So so we're gonna comment a bit on like the measurement time of this protocol. So first, so it's the first protocol to certify quantum communication through an untrusted and lossy quantum channel. And it was the first proof of principle implementation, which of course took like 1 to 3 hours to certify qubits because we had bit suboptimal quantum resources. But we showed that it could be brought down to a few seconds if we had like state-of-the-art sources, which are already allowed commercially now. So this could already be close to practical. And of course, there are a lot of applications to this because a quantum channel is not only like a single mode fiber, as we certified. You could have like plenty of different channels. These are basically anything that does the identity. So you could certify quantum memory, you can certify frequency converters. So this is what actually was done in parallel by our colleagues in Geneva. One protocol that we would like to implement in the future is authenticated quantum teleportation, because teleportation is nothing but an identity channel. So you could consider that the whole teleportation protocol is a quantum channel that you can certify with this protocol. So as I mentioned, this protocol, this work was very recently accepted in PRX Quantum. So hopefully you can see it soon there. And so if you have any questions on this, I'm going to finish the talk and we can have more questions on this. So these were like two experimental demonstration of the first experimental demonstration of two major quantum primitives, so remote weak coin flipping and transmission of quantum information through an interested channel, which are like important building blocks for other protocols. So this will be at the basis of a wider quantum network. And so, well, the message I'd like you to keep from this talk is that photonic entanglement can be used for far more things than just exposing a spy in quantum key distribution, even if it's cool already. So, for example, sanctioning a cheating player in weak coin flipping, or detecting the disruption of quantum information in certified quantum channel protocol. And there's even more things that you can do with multipartite quantum entanglements. So this is the work that I've carried out at the end of my PhD and that I've been pursuing in collaboration with the Neves, and which I'm still interested in. So here, show you like the design of a multiplex source that I proposed at the end of my PhD, and that was recently demonstrated by the now PhD students, and now, actually no, they defended now. Well, one defended. We demonstrated this source, and now various protocols are enabled thanks to this source. So the device-independent GHZ state certification was demonstrated recently, and there are plans to demonstrate far more protocols for anonymous communication, authenticated teleportation, of course. And I'm getting more and more interested in more multiplexing scheme, which makes this source of multipartite entangled states more practical. So, dziękuję za uwagę. And if you have more questions, I'll be glad to answer. Oh, and of course, this.
Ah, yes.
So, who could guess? So the first one. The first one is the easiest.
You got to go?
Yes. The second one, the artist. Doesn't ring a bell? The one?
I know the picture, but...
Yeah, it's very famous. It's Gustave Courbet. The third one. So he invented a vaccine.
Okay. So your university.
Yes,
Pasteur.
that's Pasteur, of course. And the Lumière brothers. That's it. Now we can move to the questions.
Okay, yes, so please, time for questions now. Last chance for students to get 5. Yes.
What is your source of entangled photons?
Oh, so we can show it again. It's Sagnac interferometer with a PPKTP crystal. So it's a pretty standard source actually. It's now used in a lot of things. So you have. Do you want me to give the details of how it works? It's like you have this nonlinear crystal. You pump it with this high power laser, and so then it's type 2 spontaneous parametric down conversion. So you generate a pair of photons, and in one side the photons are going to be horizontally and vertically polarized, and on the other side you're going to have the other way around. And so in one side you're going to have HV, and on the other side you're going to have VH. So you have the superposition of these anti-correlated photons. Yeah?
Superposition of two polarization.
Yes, so you have this or this. So this is for this protocol. In the other protocol, it's simply having like a single photon and you mix it with vacuum on a beam splitter, and then you don't know if the photon is here or is here.
So here is two particle entanglement, and
this is two particle, and the other one was one. It was two modes, yeah.
Okay.
I can make you the drawing afterwards if you want, because I didn't include it here.
Okay, so you said that for this you need a secure classical channel, yeah?
Yeah, it's just a classical channel.
This basically means that you in principle need QKD for this, yeah?
Yes,
because,
definitely.
like, the easiest attack would be the attack on the classical channel.
Yeah.
No,
Sure.
it's
Yeah.
not-
No, you definitely need QKD. Yeah.
And also, like, so this is a way to authenticate this quantum channel, yeah? But you need authentication of the classical channel, yeah?
Yes. Yeah.
Back to the weak coin flipping. How crucial is it to have real single photon sources? Could you use, like in QKD, decoy state method to make it more easier to experimentally do?
Like a weak coherent state, for example.
Yes, coherent states with various intensities.
So the thing is, they need to know when the coin is going to be flipped, otherwise the protocol is aborting. So this is why we had to get like a pretty high heraldic efficiency. If you use weak coherent pulses, then the abort probability is going to skyrocket, and then you lose all the point of having quantum. Like you.
Yes, but you can repeat your states faster.
So that's a very good remark, because that it was shown by like theoretician from my group, from my former group, that this protocol sadly is not composable. So it means that you can compose it with itself first to increase the security. It's a one run protocol. It's either it aborts or you succeed, and you can't repeat it to increase the success probability. Which also means that, as it's not composable, if you want to include it in bigger protocols, you need to rethink the whole security together. So that's a big problem with this protocol. It has to be known.
And it's not composable because it cannot be, or if there's no way.
It means.
For now.
Okay, so I'm not expert on composability. For this, you need to ask my colleague Raja Yaya. But what I understood is that it's not composable in general, but it means that you could possibly include it in another protocol. But for this, you can't consider the blocks, the building blocks, independently from each other. You have to consider the whole protocol together. Yeah.
Yes.
Okay. Any more questions? I was just wondering, in your fidelity curves, you compare it with 1/2 fidelity, which is the pure noise. But shouldn't you rather compare with like 2/3, which is what you can do with measuring your qubit and then sending classical information?
So that was a debate, which was classical noise in the end. But yeah, it's up to debate.
Okay.
It's more.
Because then you could argue that then you have truly quantum channel that is doing better than classical could have done.
I mean, I think we also we also achieve above 2/3 anyway. But
okay, that's
for the blue ones that.
Okay. Yes.
Yeah, but that's a good question. We had a lot of debate on this. In the end, the theoretician said no, 1/2 is good.
Okay, so last question for the semester. Who wants to have this privilege? Okay, you want vacations? Okay, good. So let's thank the speaker again.